like this. As soon as you see it, you'll get... So I suppose we do a to the 8. Okay, I've chosen 8 for a particular reason. Now, ordinarily, we do 8 copies with 7 multiplies in there.
Mm-hmm.
Mm-hmm. Now, suppose we did this. Suppose we did a squared, which is a times a. So that's 1 multiply. Then suppose we did a squared times a squared, which is another multiply. But what's a squared times a squared? That's a to the 4.
Mm-hmm.
Okay. What if we did a to the 4 times a to the 4, which is another multiply? Well, what's a to the 4 times a to the 4? That's a to the 8. Oh, hang on a sec. What does that mean? That means we've just calculated a to the 8 using 1, 2, 3 multiplies instead of 7 of them. So all we've done is, instead of taking 8 copies of A and multiplying them all out with 7 multiplications, we've said, let's do A squared first, then square it, then square that again, then we've suddenly got to a to the 8 with only 3 multiplications. Okay, does that make sense?
Mm-hmm.
Yep. So let me go back to... So a to the 100, yeah, maybe we can do something like that. So there's a couple of ways of, I mean, in mathematics, we just play with things. So there's a couple of ways of approaching this. One might be, I think I'm just, as I said, winging it as an explanation. Maybe you could do something like this and say, oh, if I could work out a to the 50 easily, then I could maybe do that, a to the 50 times a to the 50, if I knew how to do that. Okay, so how might I get a to the 50? Well, maybe that's a to the 25 times a to the 25. Okay, so again, that'd be another multiplication. That's if I could do that. Well, maybe I could do a to the 25 is a to the, well, in this particular case, what I'm relying on here is that 50 plus 50 is 100. 25 plus 25 is 50. And, or more to the point, 100 divided by 2 is 50. 50 divided by 2 is 25. 25 divided by 2, I can't do. I mean, it's 12 and a half. I don't really want to do halves as my index. But maybe I could do something like this. A to the 12 times a to the 13. Again, that would involve one multiplication. Now, each time I'm doing this, I'm saying to myself, well, I could do this if only I could do the a to the 50 easily. So let's look at the a to the 50. Well, that requires doing a to the 25 easily. How can I do a to the 25? Well, I could do that if I could do a to the 12 and a to the 13 easily. So at this stage, well, maybe I could do something like, well, a to the 12 is a to the 6 times a to the 6. Well, that'd be another computation. And to get a to the 13, maybe I could do a to the 12 times a. So that'd be another computation. Okay, that still leaves me, I've still got to work out what a to the 6 is. So a to the 6, maybe I could do a cubed times a cubed, okay, which would be another one. How could I get a cubed? Well, probably the only thing I could really do is maybe just do a times a, which is 2. So at least I can see that if I can compute a cubed using 2, then I can get a to the 6, which is another one. Then a to the 12 would be another one. Then a to the 13 would be using a to the 12 times a. So you're kind of doing a bootstrap. You're pulling yourself up by your bootstraps, and you just work your way back. And so you've got 2, 3, 4, 5, 6, 7, 8. 8 computations.
Okay.
Okay, so that's just working kind of backwards based on this idea. The other thing that you could do is to say, instead of working backwards, starting with a to the 100 and trying to break it down, maybe you could start with this idea and build up. So the idea would be, if I keep on.
13 multiples of 2, like powers of 2.
Yes. So a to the 16 is a to the 8 times a to the 8. So that would be another computation. A to the 32 is a to the 16 times a to the 16, which is another, that's another one. A to the 64 is a to the 16 times a to the 16, which is another one. Now, if I go one more step, that's going to get me to a to the 128, which is overshooting my a to the 100. So maybe I could use these to build up things. And the idea then would be, let's see, I think I've got just enough room down the bottom. So maybe I could do something like this. A to the 64 times a to the, well, if I multiply by a to the 32, what would I get? 64 plus 32 is 90. 96.
Yeah.
Okay. That gets me to, let's keep a running total. 96. Well, I need to get to 100, so 96. I could do another a to the 4. And that would give me my a to the 100. Okay, so 64 plus 32 is 96 plus another 4 gives me 100. Okay, so this was another 2 multiplications. So how many did I use altogether? 1 for the a squared, 1 for the a to the 4, 1 for the a to the 8, 2, 3. So it's 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6 multiplies to get as far as a to the 64. And now I use all these to build up things. So I've had 6 there plus the other 2. From here, again, gives me 8. So it's a different style of thing. Here I was breaking down and seeing what I could do. And here I was building up. And in fact, really what's happening is is the following. What you're doing is you're taking 100 and you're breaking it into powers of 2. So it's 64 plus 32 plus 4. So you know it's 2 to the 6, 2 to the 5, 2 squared. So you're breaking down 100 into those. And by doing that, you can say, a to the 100 is this power of a times that power of a times that power of a. And you're using this idea that because you've got powers of 2, this idea of doubling, that you can evaluate these powers of 2 powers, so a squared, a to the 4, a to the 8, a to 16, 32, 64. You can evaluate those quite easily. And because you can do those, you can break down this. I mean, suppose I wanted to do a to the 99. What I would do then is say 99 is equal to what's the biggest power of 2 that goes into 19, that's less than 99? 64. Well, that would give me 35 left over. What's the next biggest power of 2 that is less than 35? Well, that's 32. Okay. And so that gives 32 from 64 gives me 32 from 35 gives me 3. What's the next biggest power of 3? Under 3, well, that's 2, and then a 1. So what I can say is that a to the 99 is a to the 64 times a to the 32 plus, times a squared times a. Okay, so to get to a to the 64, I've gone through a squared, a4, a to the 8, 16, 32, 64. So that required 1, 2, 3, 4, 5, 6. Again, 6 calculations, 6 multiplies to get that. Sorry, I didn't put that up there. Useful if I did it this way. So 6 multiplies to get a to the 64. But those 6 also gave me a to the 32 and a squared. So I've already got those for free by having calculated a to the 64.
Mm-hmm.
Then I just need another 1 there, another 1 there, and another 1 there. So in fact, I need, this is really quite bizarre.
Yeah, you need more.
6, 7, 8, 9. You need 9.
Is it because it's odd?
It's because I need more powers of 2 to add up to 99 than I do to get to 100. So 100, I needed 64, 32, and 4, whereas here I needed 64, 32, and 3 has to be broken up.
Mm.
So I actually need the worst one that would happen is let's see, for this a to the 63. Okay, and the reason being is that 63 is 32 plus 16 plus 8 plus 4 plus 2 plus 1.
Mm.
Okay. So if you want to build up 63 using powers of 2, that's the only way that you can do it. I mean, basically, what you're saying is that 63 in binary is 1, 1, 1, 1, 1, 1. So that's really what's happening. So to a to the 63, I need to do a to the 32 times a to the 16 times a to the 8 times a to the 4 times a squared times a to the 1. Okay, so a to the 32, I actually only needed 1, 2, 3, 4, 5. So I needed 5 for that one. And I've got those for free, but I also need a multiplier there, 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 and there. So I actually need 5, 6, 7, 8, 9, 8, 9, 10. I actually need 10 to do a to the 63. That's really odd, isn't it? I mean, really bizarre. That I need more work to calculate a smaller power. But you can see that if I want to do a to the 128, I just simply go up here.
It'll be quicker.
Yeah, I'd square that. I'd square a to the 64. And the thing is that 128 is a power of 2. So I need 1, 2, 3, 4, 5, 6, 7. So I'd only need 7. So it's really all about breaking down so if I've got a to the m, it's really about breaking down m into a sum of powers of 2, and that gives you the most efficient way. And it's kind of related to this. I mean, this is not totally unrelated. It's just a different way of thinking about it. So this method, I think, If I had to guess, it either gives you what this method would do, or maybe one extra multiplication. I'd have to check that, but it would give you something pretty close to doing it this way. This is certainly gives you the optimal method, and this one might or might not. Yeah, does that make sense?
Yeah, no, that's good. Thanks. I just needed it broken down into where you broke down each of the initial breakdown of the powers.
Yeah. So the real trick to it is that you're saving to get these by doing these squarings. You're saving yourself time in calculating these powers, and then you use those to break down the original problem. Yep.
Cool.
Okay, great.
Thank you.
I had a question for you as well, Chris, if we have time.
Yeah, sure.
Yeah, 11 o'clock.
Yeah, absolutely.
So on problem sheet 16, looking at question...
Oh, hang on a sec. Yeah, okay. I'll just write it down. So problem sheet 16, yep.
Yeah, question 21, so it's log 10 to the 0.0001 equals question mark, which is 10 to the power of what equals 0.001. I'm just trying to work out how to, like, what power turns a 10 into a 0.0001. I have a feeling it's maybe a minus power. But,
yes, you're right.
And I'm like, okay, what about 10 to the minus 4? But I just don't know how to calculate that or how to convert it.
How to think about it. Okay, so just let me write this down. So we've got log base 10 of 0.0001. Okay.
Equals something.
Equals something. Well, okay, so let me just share.
I just don't want to look at the answer. I don't want to just do the cheats way out.
Yeah. Oh, let's. Well, yeah. Well, okay. Let's do a different one. I suppose we're doing log base 10. I mean, they're actually all the same in a sense. Log base 10 of. Okay. Well, let's start with 100.
Yeah.
Equals something. So really, what you're asking is.
So 10 to this something.
10 to
equals
the
100.
Something equals 100. So what do you need to put up there? Well, obviously
2.
2. Yeah. So that 2 goes there. Okay. Log base 10 of 0.01 equals something. Just put it there. So you're saying 10 to the what equals 0.01. And you say to yourself, well, this is obviously not a positive power.
Yeah.
Because otherwise you'd have 10 squared is 100, 10 cubed is 1,000. So what you might do is something like this and say, well, what powers do I know? Well, I know that 10 squared, I'll actually do it this way. It's a bit long, but I think it helps. 10 squared is 100.
Yeah.
10 to the 1, which is just 10.
Yeah.
What's 10 to the 0?
10 to 0 is 1.
1, yep. So as we're going this way, what are we doing?
Oh, okay. So we're
10.
getting rid of a 0, and then so 10 to the negative 1 will be 0.1. Is that right?
Exactly.
Yeah,
exactly.
And then 10 to the negative 2 will be 0.01.
Mm-hmm. And how does that help you?
By you just keep extending it out. So so 10 to the negative 4. Okay, that makes sense. I just wasn't sure. Like, I knew it was something like 10 to the negative 4, but I wasn't sure how it got there. But thanks for explaining that.
Okay. Yep. So the idea is that as you increase the index by 1, you're multiplying by 10. As you're going backwards, you're dividing by 10. Okay.
Yeah. Okay.
Good.
Thank you.
Excellent. Yeah.